the nature of how currents and charged particles behaved in magnetic fields. We talked about torques, we talked about forces, we talked about... Excuse me. I can tell spring is coming in full swing. I'm taking my allergy pill every day, and it's absolutely dominating me right now. So just going to hold on to my coffee and hope to wash away all of the allergy pain in caffeine and bitter notes of overcooked coffee. So we're ready to do some problems, and then we're going to talk about, as I promised you last week, we're going to talk about where magnetic fields come from to begin with, because at this point we've just said that, hey, there is such thing as magnetic fields, they exist. Trust me on that, and we'll move on with our lives. Well, today we're going to actually talk about where they come from and the nature of those fields. But as far as we're concerned right now, what is the maximum torque on a 400-turn circular coil of radius 0.75 centimeters that carries a current of 1.6 milliamps and is in a region with a uniform magnetic field of 0.25 Tesla? And what we said last time, if you haven't gotten the Quickly code, I'll put it back up here after we get this problem done. We said last time that the magnetic field, the torque exerted by a magnetic field on some loop is going to be mu crossed into B. Mu crossed into B. And what did we call, or what did we name that little variable mu? Does anybody remember? It's not the 151st Pokemon, contrary to popular belief. It's the magnetic moment, right? The magnetic moment, which we said mu is equal to N times I times A times N hat, right? So if the current loop looks something like this right here, lying in the plane, then the normal vector is going to be in this direction. It's perpendicular to the plane of the loop, right? And this is going to be the radius. We'll call this R, and this is going to be the radius R right here. And so we need the area. That's going to be equal to pi R squared. We're given the current. The current is I right here. And then N is going to be what value? This big N. Does anybody remember what big N is here, William? The number of loops. So this variable given to us right here is N, big N, the number of turns in the loop. It's looped over itself 400 times, therefore we're going to use 400. Now, if we're saying in part A here that torque is equal to mu cross B, then we also said that, that this is going to be equal to mu B times the sine of the angle between them. And let's just concern ourselves with the magnitude of what that vector is going to be. And it asks us, what is the maximum torque here? Well, according to what we've been given, mu is going to have a fixed value. B is going to have a fixed value here. How do I get maximum torque, considering that the only thing that's variable is theta? When sine theta is equal to 1, when the angle between the magnetic field, so this is maximized when mu is perpendicular to B, right? So that means that B is likely going to have to be pointed in, let's say, this direction right here. So this is going to be B, pointed in this direction. And that's going to be perpendicular to my magnetic moment, which is pointed in the direction of N. If I could get these all parallel, that would be wonderful. So we just want that the maximum torque is equal to mu b, or that's equal to N times I times A times B. So that's 400 times 1.6 milliamp is 1.6 times 10 to the minus 3 amps times an area of pi times R, which is going to be, 0.75 times 10 to the minus 2 meters squared times the magnetic field strength of 0.25 Tesla. And this gives us a maximum torque of, 28.3 times 10 to the minus 6 Newton meters. Or you could say that that's equal to 28.3 micronewton meters. Micronewton meters. So a tiny amount of torque, right? I mean, you're not going to see this thing want to immediately tip over unless it's on some sort of frictionless pivot or something like that, in which case it might tip over, or it would tip over, but very slowly, depending on the mass of the loop, the mass of the wire that creates the loop. Questions on this one? More or less straightforward. Okay, so the question was, where did sine theta go, essentially? Sine theta, mu and b are fixed values based off of the values given in the problem. So that means the only thing that is variable in terms of finding the maximum torque is the angle theta. And we said that theta is, sine theta is maximized when theta is 90 degrees. When theta is 90 degrees, sine of 90 degrees is 1. So it didn't really disappear. It's just that we let sine theta go to 1 to get a maximum amount of torque. If theta was 0, then the sine of 0 is 0, and you would get 0 torque. Yep. Good question. Okay, next problem. A rectangular current-carrying 50-turn coil is shown in the figure and is pivoted about the z-axis. The z-axis, which lies down here, going into and out of the plane, if you will. If the wires in the z equals 0 plane make an angle 37 degrees with the y-axis, which is just what's drawn right here, what angle does the magnetic moment of the coil make with the unit vector I hat? Write an expression for n, the normal vector, in terms of the vectors I and j, where n is a unit vector in the direction of the magnetic moment, and see what is the magnetic moment of the coil. And finally, what is the torque on the coil when it is in a magnetic field B that is equal to 1.5 Tesla pointed in J hat in the region occupied by the coil. Find the potential energy of the coil in this field. So the first thing that I want to figure out is in what direction, or excuse me, what angle does the magnetic moment of the coil make with the unit vector I hat? Does anybody want to take a stab as to what that value should come out to be? your options are going to likely be either 0 or 90, or 37 or its complement. Whatever 90 minus 37 is, that's 53, right? No, 43. So your options are 0, 43, 37, or 90 degrees as a multiple choice test question. What is 53? So that's going to be one of the good options. It's not going to be 0 because we'd expect the normal to be coming out of the loop kind of in this direction, right? So it's not going to be 90 or 0. It's going to be 43 or 37, right? So we want to figure out which one it's going to be. Let me reorient this problem for you. And let's draw our y-axis like so. And let's draw our x-axis like this. So this is x. And then the plane of my loop is going to be oriented like so. So these are, you can imagine that it's going down along this front side here. So the current I looks like so. And we had to orient an angle 37 degrees like so. And the normal, which is going to be perpendicular to this loop, in this case, is going to be pointed down like so. That's n hat. And x I hat is going to be pointed in this direction, right? It's going to be pointed in the x direction. And so now we want to consider if this loop were still aligned to the y-axis right here, if we moved this loop from this angle of 37 degrees along the y-axis, what you would see is that as the loop goes to this configuration right here, that n hat, in that case, is going to be pointed in the I hat direction. And so whatever angle that we orient away from the y-axis, I get the same angle theta right there as my orientation away from I hat. So in this case, to answer part A, I get that if the wire is at angle 37 degrees, what angle does the magnetic moment make with the unit vector I hat? It's still going to be theta, which is 37 degrees here. If it is difficult to understand what's going on in a problem based off of a 3D configuration, try some of the 2D projections of the three-dimensional problem to get an idea of what's going on here. The most logical one is where you're looking down the z-axis, which is what I've drawn right here, in which case I've got that loop angled 37 degrees away from the y-axis. So any questions on what we calculated there? William? Okay, so how do we know that n is pointed down and to the right instead of up and to the left, essentially, right? So one of the things that we're going to discuss today is, since this has some current I in it, that's how we determine what direction the magnetic moment is. What we're going to discuss today that we haven't gotten to yet is using the right-hand rule to figure out what direction the magnetic field coming from that current loop looks like. And it's going to be the same direction of the magnetic moment. So the way that it works for this, choose any one of the four sides that you find here on the loop. So what I'm going to do is I'm going to choose this top side right here that lies in this direction. And when I do so, you want to align your thumb in the direction of the current. So my thumb is going to be going down and to the right, or coming towards the left of the board here, the left of the screen. My thumb aligned to the direction of the current. And then the direction that you grasp the wire, the directions that your fingers curl when you grasp the wire, is going to be the direction of the magnetic field generated by that current loop. So I grasp the wire, or another way you could think of it is my thumb aligns to the direction of the current, and then I reach with my fingers towards the point that I'm trying to measure the magnetic field at. So I'm going to reach towards this point right here. The direction of my palm, or the direction of my finger curl, is the direction of the magnetic moment, which in this case is going to be out this direction of the loop instead of going the opposite direction that you suggested. Another way to consider it is if I look at this projection right here. Now I align my thumb down along the direction of the current, and I reach into the screen to figure out as to the point that I'm measuring the magnetic field or the magnetic moment, and my palm points down and to the right in that case, giving me the direction of my magnetic moment. I wanted to give you a preview of that because that's what we're going to be talking about here in just a second, but since we didn't know that a priori, most of the problems are going to be set up in such a way where the magnetic moment is going to be between parallel to the magnetic field and perpendicular to the magnetic field. We'll practice that here in a second. Part B, write an expression for n hat in terms of the unit vector I hat and j hat. Essentially, what we're trying to do is how much of n hat is going to be pointed in the I direction and how much of it is going to be pointed in the j direction. And what you get is that n hat, if I zoom in here, let me look here at, let me draw another set of axes. So this is going to be y, and this is going to be x, and n hat is pointed, nope, why did it draw that backwards? N hat is going to be, that's so bizarre, is going to be pointed in this direction. And so we want n hat in the x direction, and then we want n hat in the y direction. So n hat is going to be n hat in the x direction times I hat plus n y times j hat. And so how do I get those particular components here in terms of I hat, j hat, and the angle theta? Well, n sub x, if this is the angle theta inside of here, n sub x is the adjacent side to theta, so that's going to be equal to n, which has unit length 1. So n has magnitude 1, so just the cosine of theta times I hat. Then we go down along the negative axis, so that's minus, that's the opposite side here, sine theta, j hat. That's it. Because I've got, why is it minus sign? Because I'm pointed along the negative j direction. Now, someone proved to me very quickly in one sentence that n hat, if this is what it is in terms of I and j, that n hat does have unit length 1. How do you prove that it has unit length 1? Yes, exactly. If you didn't hear that, just like we find the magnitude or length of any vector, take the x component squared plus the y component squared. So cosine squared theta plus sine squared of theta, that's equal 1. Then you take the square root of it. The square root of 1 is still 1. So yes, n hat has unit length 1. We've at least preserved that property here. Part C, what is the magnetic moment of the coil? Mu is going to be equal to n times I times the area of this loop here, A, which if we call this our width and 8 centimeters our length, so that's going to be n times I times the area, so length times width, times the direction of the magnetic moment in hat. So this is going to be equal to 3 turns is what it's showing here. Oh, 50 turns, sorry. 50 times the current I, which is 1.75 amps given in the figure, times the length of 0.08 meters times the width of 0.05 meters times in hat, which comes out to be equal to, if I could scroll down just a wee bit, 0.2795 I hat minus 0.2106 J hat. And that's going to be an amp meters squared. 50 is unitless and hat is unitless. I've got a current in amps times meters, so that's where I get a magnetic moment of amp meters squared. And part D at this point, part D, is just going to be torque is equal to mu crossed into B. Remember that B, you can't see it anymore, but B is going to be equal to 1.5 J hat, Tesla that is. So that means that whatever is crossed into this direction here is going to go away, right? Because a J component crossed into another J component, that doesn't matter. So we get I crossed into J. Our torque should be in the Z direction. So I get that my torque is equal to 0.419 K hat. And that's going to be, everything's in standard SI units, so it comes out to be Newton meters of torque. And then E, maybe you remember, maybe you've forgotten at this point, is equal to minus mu dotted into B. So I get minus, the J component is the only thing that survives. So I get negative times negative gives me positive, and so I get 0.316 joules for the potential energy here. I've got Bluey on the brain this morning. I wanted to finish that problem and say wackadoo, just like Chili does. Listen, I know college is stressful. If you want a good, wholesome 8-minute per episode show just to kind of decompress at the end of the day, watch some episodes of Bluey. It's a good way to do it. You don't have to have kids to watch Bluey. It's got motifs that adults can appreciate too. All right. What else do we got? Let's do a problem using the Hall effect. Right? So we've got the metal strip, which has a width of 2 centimeters and a thickness of 0.1 centimeter, and the current flowing from the back side of that strip to the front side of the strip. And we get that B, the magnetic field B, is going to be going through the top of the strip here. So absent of whether the charge carriers are positive or negative at this point, do you expect the charge carriers to be deflected towards, let's say, the top-bottom direction of the strip here, towards the left-right direction, or towards the front-back? This Hall potential is going to cause, or the magnetic field is going to cause a deflection in one of those three principal directions, towards the top-bottom, towards the left-right, which is AB, or towards the front-back. In what direction do you expect that deflection to occur? It would be towards AB. I mean, simple enough with them asking you that in the problem, but again, if you didn't have an intuition about that, take I, so I is going to be the direction of the current, and cross it into B. So I crossed into B, I point my middle finger in the direction of I turn my palm in the direction of B, and my thumb is going to be the direction of the deflection, so towards AB. So that's going to be the direction of our Hall potential. And here, what we're told is instead, the Hall potential is 0.27 microvolt, and the magnetic field is this. And it wants us to know what is the drift speed of our charge carriers. And what we said last time is that the Hall potential that you get, the perpendicular deflecting potential, is going to be equal to the drift velocity of your charge carriers times B times the width, which is this value right here. We called this the thickness T. So times the width. And all we have to do is solve for our drift velocity. So V sub D is equal to the Hall potential divided by magnetic field strength times width. So V sub D is equal to 4.27 times 10 to the minus 6 volts divided by a field strength of 2 Tesla times the width of 0.02 meters, which gives us 1.07 times 10 to the minus 4 meters per second, or that's 107 microns per second. Microns are micrometers. But for some reason, we say micro everything, except if you're in the field, you'll hear microns for micrometer. That's the only one that gets a shortened name. And if people, I once said micrometers in the lab, and people scoffed at me for using the wrong name. So it's one of those arbitrary things in the science and engineering field that if you know, you know. So to prevent you guys from being scoffed at in the lab, it's microns, not micrometers. Because someone somewhere along the way decided it was so. Yeah, that's how most things are, right? Okay, part B, find the number density of free electrons in the strip. It turns out that this comes from last unit. What we said last unit is that net current I is equal to charge number density times area, cross-sectional area. Times the charge of an individual carrier times the drift velocity. Or in this case, if you're trying to find the number density is equal to current I times A times charge of the current carrier, of the charge carrier, that would be E in this case, times V sub D. And the cross-sectional area is going to be the area of this right here that I've drawn out on the end of the screen. Ooh, you can't see that at all. Let's see if I do it this way. This is the area perpendicular to the direction of the current here that's kind of hashed in black. So that's going to be equal to T times W. So I is divided by TW times EV sub D. If you multiply all of this out, you end up getting, let's see, let me scroll down here. You end up getting that N is equal to 5.85 times 10 to the 28 per cubic meter. So we get, what would that be? Over 1 billion electrons per cubic meter here. 100 billion electrons per cubic meter. Pardon? E is the elementary charge, yes. E right here is that 1.602 times 10 to the minus 19 coulombs. Now, is point A or point B at the higher potential? We know that the potential difference from A to B, the potential difference is 4 point whatever microvolts, right? Which one is at higher potential, A or B, in terms of the Hall potential? And I don't remember, this is not an odd numbered problem, so the answer wouldn't be in the back of your book, but the solution in their solution guide is actually wrong on this one. They got it backwards because of a common mistake. Is A or B at higher potential? Part C is saying V at point A is less than V at point B, or V at A is greater than V at B. Okay, so how did you calculate that? Yeah, you're going. Yes, so if you can't hear what William is saying, you've got electrons here that are traveling this, let me use a different color, that are traveling this direction here through the material, right? So if I take V, my middle finger aligns to V going into the screen, crossed into B, I get a force to the right, but electrons have negative charge. Therefore, we expect the force on this to be to the left. So you've got more electrons over here on this side than you do leaving positive charges over here on this side. So that means that VB is going to have higher potential than VA, because positive charges are going to create areas of higher potential, negative charges are going to create areas of lower potential. So VA is less than V sub B, or another way to say it is the potential at B is greater than the potential at A. How did I determine that A had the side of negative charges? Again, we said that the force on a moving charged particle is equal to Q times V crossed into B. And don't forget here that the charge of the charge carrier is minus E, right? So if I take V cross B, V crossed into B is going to give me a force to the right, but then I have to flip that over to the left here. So this is going to be the direction of the force F. And so if there's a force acting on these electrons to the left, then all of the electrons that flow through it are going to be pushed up against this left-hand side here. Spring break is next week, right? That's what I was thinking. My brain can feel it. I have had 2 or 3 cups of coffee this morning, and I got 9 hours of sleep last night, and I'm still wiped out. It's time for spring break. Any other questions on this one? All right. Let's switch gears then. This is always interesting to me that people can listen to pop rock or other and still study. There is a correct answer to this one. The correct answer is the last one. There have been many, many studies shown that listening to music while trying to perform a mentally strenuous task, such as studying, actually your brain can't multitask and it gets distracted by the music. It's really fascinating stuff. You should look it up. But I'm not going to chastise you for listening to music while you study. I listen to music while I write exams and while I grade and while I do research. I just like having soft, like classical music going in the background while I study. I can at least mostly tune that out, unless it's Beethoven's Fifth or one of Mozart's pieces that's very famous. I usually just skip it then. Just curious. So we're ready to discuss now where magnetic fields come from. Where do magnetic fields come from? That is the question, right? Magnetic fields, in general, are created according to this law down here, which is known as the Biot-Savart law. The Biot-Savart law, which states that the magnetic field is equal to mu naught over 4 pi times QV cross R divided by R squared. So let's unpack that a little bit. Mu naught is known as the magnetic permeability of free space. The magnetic permeability of free space, which is defined as 4 pi times 10 to the minus 7 Tesla meters per amp. Q is the charge of the moving charged particle. So if it's a proton, it would be plus E. If it's an electron, it would be minus E. If it's anything else, you'd have to be given what the charge of that carrier is. V is the direction that the particle is traveling, and R hat is the direction from where the charge is to the point in space that you're measuring the magnetic field strength. So V is the direction or the velocity of the moving charge particle. R hat is going to be the direction from the moving charge particle to the point in space where you're measuring the magnetic field strength. And then R squared will then be the distance between the charged particle and the point that you're measuring, that distance squared. So it's very similar to Coulomb's law for the electric field of a charge. The only problem is you've got this cross product in here. So you reach out towards that point because you want to take V and then cross it into B, and it's going to give you, as is shown on the screen here, at least for this configuration, that B is going to be into the screen for that point. V is into the screen for the single point chosen here. Actually, if you look at any point that is on the plane of the screen here and to the right of this green velocity, then you would get that B is going to be into the screen there. But if you were to look to the left of the vector V, B would be pointed out of the screen in that case. If you take V and cross it into any point B, then you would get that at that point to the left of V, you would get B is pointed out of the screen. So what's going on here? If to the left of V, you would get a magnetic field pointed out of the board, and to the right of V, you get a magnetic field pointed into the board. What is this telling us? And what am I maybe very quickly glossing over or not explaining? What's going on if it can be out of the screen on one side of V and into the screen on the other side of V? What is the nature of the magnetic field? What's that? It is circular. Yes, the magnetic field forms loops. So what's actually happening here is if you look to the right of V, it's going into the board. But now let's look at a point behind V. A point directly behind V. You take V, you cross it into that point. That means that the magnetic field would have to be going to the left side of the screen, behind V. And then we come out to the left side of the charged particle. Well, I take V and I cross it into that point that's going to be to the left of V. I get one that's coming out of the board. If you look in front of V, it's going to be to the right of the screen. And so you get these loops that are going into and out of the screen, going into the screen to the right of V, and coming out of the screen to the left of V. So just to reiterate, a point charge is moving at constant velocity. What best describes the magnetic field it generates? Good. If you're having trouble visualizing this, maybe my next graphic, it was the best one that I could find that had a Creative Commons license, will give you an idea of what the magnetic field looks like. So you get here that if V travels around one direction, choose R to be the direction towards any point here going around the charged particle. Then taking V and crossing into R will give you the direction of B, and so you get these subsequent sets of loops here that go around the charged particles. So you could think of it as a cylinder. The cylinder is going to have the highest strength perpendicular to the charged particle, to where it is now, and it's going to decrease in strength going out in front of or behind the charged particle. But you still get that it's going to be a cylinder that wraps around the direction of V. It's going to be a cylinder that wraps around V. And the direction that you could imagine the magnetic field looping around that cylinder is going to be given by this cross product of V crossed into R. Unfortunately, we don't have that charged particles have to be moving with constant velocity, which means that their speed can change or their direction could change. which again implies the need for an integral. And this actually is the Biot-Savart law in its complete form. The Biot-Savart law is written for differential amounts of current, where a differential contribution to the magnetic field at some point P is equal to mu naught over 4 pi times the current I times dl crossed r divided by r squared. And here's the problem, is that r squared is going to change depending on where along the current you're integrating. So these problems get very difficult very quickly. And they're not fun when you get into E&M for upper level physics majors, or especially for graduate students. But for most of the problems that we're going to be doing here in this class, we're going to be dealing with currents and velocities that are constant in direction and magnitude. So you could integrate around that loop. One of the cases that we'll deal with here in this class, we find that the magnetic field of a current loop integrating around this loop here, where we'd get that R is going to be constant, making this a much easier problem to solve. You get that the magnetic field of a current loop only at the center of the current loop. So this is a very specific case, so a circular current loop, and we're only finding the magnetic field here where the current, where the cursor is equal to mu naught I divided by 2R times Z hat. And this comes back to the question that William asked about what is the direction of the magnetic moment. It is found using the Biot-Savart law here. Take the current I and cross it into the field point that you're trying to calculate. So let's choose this. We take I hat is going in the x direction here. So the current is going in the minus x direction, so negative I hat. R hat is going to be negative j hat, so negative I hat crossed into negative j hat gives us a magnetic field that points in k hat, out of the plane here of the loop. So I'm not expecting you to be able to do this integral yourselves. This is the same case of when we did Coulomb's law before, where we did those big nasty integrals, where we did Gauss's law and big nasty integrals. Here's the result if you were asked to solve a problem for the magnetic field inside the center of a current loop. This is what you will use. If you have to find the magnetic field loop along the z-axis, anywhere above or below the current loop, then the net result is that the magnetic field along the z-axis is mu naught over 2 times r squared I divided by z squared plus r squared raised to the 3/2 power. And you can see where I kind of work through that here. And the reason that I say that B is only pointed in the z direction is that if you imagine that dB is pointed up and to the right along the z-axis, just from this single amount of current, there is a symmetrical piece of current down here on the bottom side of the loop where the magnetic field will be pointed down and to the right, and all of the components except those that lie on the z-axis are going to cancel out. And so for this very specific case, you get a magnetic field that on the z-axis only points in the z direction. The sine theta term, you end up I think the confusion here is there should be an integral term out in front. No, I guess not, because sine theta is going to be equal to, in this case, if you look at theta is right here, the sine of that is going to be r divided by the magnitude of the hypotenuse, so big R divided by little r. So I've got big R. Little r is going to be z squared, so the distance from the origin to this point squared times big R squared. So sine theta is this last fraction here, just using the trigonometry. The last slide was just at the dead center of the current loop. So the question you should ask yourself is, does this solution here lead us to the solution on the last slide? In fact, it does, right? Take this solution and set z equal to 0, which is the case for the last slide. Well, in that case, when z goes to 0, r squared raised to the 3s power is r cubed, so you get r squared over r. Yes, we get mu naught I over 2r, just like we did on the last slide. So this case includes the case from the previous slide when z was 0. Good. Now what you can do is you can stick a lot of those loops together, side by side by side by side, and as you align those loops together, then effectively what you have created is a solenoid. Or if you're from the south, a solenoid. So if you stick a bunch of current loops together, or another way to think about it is you wind that that wire over some cylinder, which you could effectively think of as having a bunch of loops stuck together. Then as we do that, we get the solenoid. And if that solenoid is long and straight and has constant cross-sectional radius r, then you could show that the magnetic field inside that solenoid is constant as being equal to mu naught times n times I, where little n is the number of turns per length. So say, for example, I can fit 50 turns of wire in per centimeter along the axis of my solenoid. So right here, let's say if I could count up the total number of turns here, I'm going to estimate that there are about 30 turns shown here. And let's say the distance from front side to back side is going to be equal to, let's say, 10 centimeters. Then I'd have 30 turns per 10 centimeters, and that would be my value for little n here. 30 turns per 10 centimeters. Now, I just want to tell you, this magnetic field is shown here as being not constant inside of the solenoid. And that's because this solenoid does not meet the condition in the second paragraph here. That is what I'm trying to say, is that the magnetic field is only constant inside of a solenoid if that solenoid is long and straight and has a whole lot of turns in it. Okay? We're talking about an ideal solenoid here. It's long, straight, and has many turns. If you break any of those assumptions, then the magnetic field inside that solenoid is not going to be constant. But for all the problems we're going to work, it gets really complicated if you break that assumption. So we're going to assume that the solenoids that we work with are long and straight. So, which of the following best describes the magnetic field inside a long current-carrying solenoid? I'm sorry, it does not form the shape of a bear. You could potentially turn a set of wires. There's your extra credit assignment. Find the configuration of current carrying wire that you need to get a magnetic field that when looped in on itself forms the shape of a bear. Yes? Little n is the number of turns you get per length along the axis of the solenoid. So the interior magnetic field is uniform and directed parallel to the axis of the solenoid. The solenoid can be thought of as many closely spaced loops of current. By the Biot-Savart law, the combined effect of these loops creates a strong, uniform magnetic field inside running parallel to the solenoid's axis. If you've ever heard someone use the term electromagnet, generally what is going to be used as the electromagnet is going to be a solenoid. Because what we get here and what you can possibly see is that the magnetic field that's generated from this looks like the magnetic field of a bar magnet. So what's the benefit of using an electromagnet that looks like this over a bar magnet? Yes, both of you are correct. You can turn it on and off, and you can change the strength of it, because the strength depends on how much current is flowing through it. So now you can turn it off if you don't want the magnetic field present, which is really valuable in some scenarios. Just turn the thing off. Or if you want it to be stronger or weaker, then change the current flowing through it. Or better yet, reverse the current in it, and you reverse the polarity of the electromagnet, right? If instead of having the current coming out this direction and coming in this direction, if I reverse that current, then I would get a reversal in the magnetic field direction, which again is really convenient depending on your application. The magnetic field of a straight wire, a finite straight wire, I should say, is again calculated from the Biot-Savart law, and I'm not going to go through the derivation here. It's actually very similar to the derivation for the finite straight wire that we did for Coulomb's law for force and electric field. And you end up getting, instead of cosine terms, you get sine terms, and you get B, or maybe we got sine terms before. We got sine terms before because we found when it was long and straight, the sine of pi and, I guess it was cosine terms. Regardless, you get B is equal to mu naught over 4 pi times I over R times the sine of theta 1, theta 2, which are shown here on the figure. And when the wire is long, meaning essentially infinite, the magnetic field of that long wire is mu naught I over 2 pi R. This is going to be a value that we're going to use over and over and over and over again. That the magnitude of the magnetic field for a long straight wire is mu naught I over 2 pi R. Yes? If it were a curved wire, you would have to go back and redo the integral. The solution here, the B, presupposes that that the wire was straight. Yep, good question. Yes, Bill? All of the equations, the final solutions that I've just shown or derived here are on the equation sheet, which will be on the test, yes. Mu naught I over 2 pi R. And in what direction is that going to be pointed? Well, take here, they show that the magnetic field is pointed out of the board here. Again, align your thumb in the direction of the current. So for us, that's going to be pointed to the right. And reach your hands in the direction of P. So that's going to be pointed up. And then your palm is going to be the direction of the magnetic field, or the direction that your fingers curl when they curl 90 degrees. So that gives you a magnetic field that's pointed out of the board. Okay? That's how they knew the direction was out of the board here. And again, you can think about that as wrapping around the wire. So you can imagine it coming out of the board above the wire, curling out, pointed down towards the floor of this classroom in front of the wire. As you go down below the wire, it's going to be pointed into the board. And then behind the wire, it's going to be pointed up towards the top of our classroom here, towards the top of the screen. R is the vector pointed from a point on the wire to the point where you're measuring the magnetic field. Yeah, so pointed from the wire to the point where you're measuring the magnetic field. So, the two wires shown in this figure carry equal but opposite currents. At the midpoint between the currents, the magnetic field is 0 into or out of the screen toward the top or bottom of the screen. That's actually on the next slide. All right. This question does usually fool people. It is out of the screen in this case, right? Let's start with the wire on the left. I align my thumb in the direction of the current. I reach towards the point. My magnetic field is pointed out of the screen here, in the direction of my palm. Now if I look at the wire on the left, I align my thumb to the direction of the current. I point my fingers towards the direction where I'm measuring the magnetic field strength. My magnetic field, again, my palm, again, points out of the screen. So both of them add together being out of the screen. Yeah, so the right-hand side, my thumb is here towards, in the direction going up towards the top of the classroom. I reach my fingers to the left. The point that I'm measuring is to the left of the wire on the right. And my thumb then, or my palm is pointed out of the screen. So that means that the magnetic field is out of the screen here. For the wire on the left, my thumb has to point down. My fingers point to the right to reach towards the screen. And so again, I get something that's pointed out of the screen. I can post a few videos that I found at Harding that will give you practice on the right-hand rule. Actually, the one time that I rickrolled all my students, I posted an announcement of like, here are 5 great videos to help you understand the right-hand rule for each of these different scenarios. And the last one, if you clicked on it, the 6th video, just took you to Rick Astley's song. It was awesome. What? Yep. Okay. So yeah, there's the explanation. This was not in the slides posted on Canvas. This is a new slide, so if you want to take a quick picture of that, but I've already walked you through what this slide says. Now if instead the current were in the same direction, both currents were in the same direction, at the midpoint between the currents, the magnetic field is pointed in what direction? Toward the nearest bear. If only we lived in a universe where magnetic fields always pointed towards the nearest bear. Which means that there would be magnetic monopoles, right? Because magnetic fields have to terminate somewhere. They terminate on the bear. And you'd have magnetic monopoles. So it's up to us to find what the magnetic plus charge is, because magnetic fields would terminate on bears, so they'd be negative charges. Magnetic plus charges would be what? What is the opposite of a bear? An anti-bear? Yeah, a bear's antiparticle is a baryon. I love it. Yeah, so baryons are going to be the antiparticle for bear. That's awesome. Well done. We have discovered a new universe of physics. That would have made for such a much better version of what was the Marvel movie with what was it? Doctor Strange in the Multiverse of Madness, or a more appropriate name for that, because that movie wasn't about Doctor Strange, it was about Wanda. My name for that movie was Doctor Strange and the Mad Mom in the Multiverse. That's a better name for that movie. And they showed like 6 multiverses in that first scene where they jumped through all of them, and then that was it. Like, what? That didn't... I'm a little bitter about that if you can't tell. So now the reason that it's 0, if both currents are pointed in the same direction, one is going to be into the screen, one's going to be out of the screen. Oh, the polar bear is the magnetic bear. I love it. This is becoming a really awesome universe that we could design. Man, so many puns. So many people are going to make excellent parents someday. I don't know. The bear itself is the pole. So the whole bear is magnetically negative. I love it. Yes, Ursa Major would always have magnetic field lines pointed towards it, and Ursa Minor would have fewer magnetic field lines pointed towards it. Well done. We've discovered a new branch of physics. Polar bear physics. Baryonic physics. Let's see. So here's where things start to get complicated, right? So currents produce magnetic fields. That's what we just discussed. But currents experience forces from magnetic fields. So that means between 2 opposite currents, what you end up getting is a magnetic attraction or repulsion between 2 different currents. Okay? So what this is saying, the differential force acting from current 1 onto current 2 is equal to I2 crossed into a differential segment of I2, crossed into the magnetic field produced by wire 1, but B1, as we've already discussed, B1 is due to wire 1. And the net result of all of this that you can try to reason through based on the figure is that if 2 currents are pointed in the same direction, you end up getting magnetic attraction between them. But if 2 currents are pointed in opposite directions, you end up getting magnetic repulsion between them. If 2 currents point in the same direction, you end up getting magnetic attraction between them. The wires want to draw together if the currents go in the same direction. Sorry, odd ringing from the microphone when I put my hands together, creating a funnel for the sound waves, I guess. I don't know. Or maybe it's where I'm standing. What? Same direction, they end up being attracted to one another. If the currents flow in opposite directions, they repel one another. Right? You can see that from, figure out what the magnetic field from wire 1 is, align your finger in the direction of the current of wire 1, and then I reach towards wire 2, my palm points into the screen, or it curls into the screen, so the magnetic field as drawn from wire 1 is pointed into the screen. Then what you have to do is take I and cross it into B, so I2 and cross it into B at that point. That gives me a force to the left back towards wire 1. Question here?
I guess it's sort of related. Are the charges running through a wire affected by the magnetic field as they create themselves?
So are the charge carriers affected by their own magnetic fields? No, that's a good question. They're only affected by external magnetic fields. So yeah, the magnetic field generated by wire 1 does not affect the charge carriers in wire 1. Yeah, it's thin energy, infinite energy, yeah. Perpetual motion devices are real. Get to work, mechanical engineers. Come on. Do what? Yeah. Big engineering is telling me that perpetual motion devices don't exist. Don't fight the system, y'all. 2 parallel wires carry current in the same direction. Wire 1 has current I, while wire 2 has double the current. Which wire experiences the greater force? Thank you to the one person who put wire 3. I put that up there for the person who always asks that question when I have Q&A pop up. Wire 3 is not the right answer. The correct answer is that they experience the same magnitude force. Right? You could do the math, the setup that I had on the previous slide, and you end up getting the same variables at play, giving you the same magnitude force. Or the simplest way to understand it is Newton's third law. If wire 1 exerts a force on wire 2, then wire 2 has to exert the same but opposite force on wire 1. That's it. Don't forget what you learned in Phys 1. As much as I know you want to brain dump Phys 1, please don't brain dump Phys 1. Ever, but especially not for this class. When a current is passed through the wire in the figure, will the wires tend to bunch up or will it tend to form a circle? This question was actually asked in the last class period. Yeah, it wants to form a circle, right? I mean, you choose any 2 adjacent points on the wire. So let's say this point right here where the cursor is and right here. So these 2 points. The current will be flowing in opposite directions. And we said that when current flows in opposite directions, you get a repulsive force between them. And so the net result is that you end up getting the wire wants to spread out. Don't do this in the lab. Don't just throw some sort of 10 gauge wire on the ground or extension cord on the ground and try to pump like 100 amps through it. That would not be good. Don't do that. You'll catch something on fire, and someone somewhere will be angry at you. The last thing that we need to discuss is, as far as has ever been measured for a closed surface, the net magnetic flux through the surface is 0. Since Gauss's law states that flux is proportional to the charge enclosed and the flux is 0, then the net magnetic charge is always 0. Or again, in at least our universe, there are no magnetic baryons that exist. No magnetic monopoles. Wherever there is a plus charge, you will always and ever see a minus charge. Or wherever there is a north pole, there will always and forever be an associated south pole. Magnetic field lines, another way to think about this, always form complete enclosed loops. I'm going to spend the rest of the day thinking about magnetic bears. It might be on the test, yes. One could say I can barely think of anything else right now. Thank you. I'll be here all day. Any questions before we wrap up here? Bears, the Bears. English or Spanish? I prefer English. I'm much better at English. I had to practice my Spanish on Sunday. That was a bit of a stretch for me. Let's see. Why is the bear a magnetic pole? Did it eat magnets? No. If it ate magnets, it would not be a monopole. It's only a monopole because in this strange universe that we devised, the magnetic field lines point towards the bear based off of that random question that I asked. I appreciate whoever put this. Y'all have a great day. I will see y'all on Thursday.